so applications of the second derivative test. At some point here, we need a second derivative to play with. But the key values we're going to use as far as what we're going to plug into that second derivative will actually come from playing with the first, because we're going to look at critical numbers basically for the first. So what I'm going to do here, I'm going to divide the problem up into two parts. One side is going to be devoted to the first derivative. So over here, if I find f prime of x, pretty straightforward to take, we know that's going to equal 4x cubed minus 12x squared. And since the second derivative will also be important over here, let's take the second derivative. Taking the derivative of the first, we've got 12x squared minus 24x. All right, so as I said, critical numbers play an important role here. We basically need to find the critical numbers, take those values, and plug them into the second derivative and see what happens. So critical numbers come from playing with the first. Specifically, here, we're going to look at where the derivative equals 0. As far as critical numbers are concerned, the does not exist side wouldn't be applicable. So if you set this equal to 0, and we solve, looks like we can do some factoring. We could factor out a 4 and an x squared. Got x minus, that'd be 3 left. So set each factor equal to 0 and solve. 4x squared, if that equals 0, then x has to be 0. And x minus 3, set that equal to 0 and solve. X has to be 3. So you go back to your notes on the second derivative test. There's your values of c. We're going to take those values of c. We're going to plug in to our second derivative. So take 0, plug in. Take 3, plug in. All right, as we plug in 0, well, we're going to get 0 back. And since 0 is not positive or negative, right, and the second derivative test is based on where the second derivative is positive or negative, then we're not going to have any extrema here. But we find when we plug in 3, we'll plug in 3, do the math, should get 36 back. That's positive. So when it's positive, let's go back to the test here. It says if f prime of c equals 0, so we found our value of c, that value of c was 3, right? And we plugged in that value of 3 here to find that this is positive, then the function has a local minimum at c. So the conclusion we could draw here, we could say, therefore, when x equals 3, we have a local or relative minimum. And now that minimum value is going to relate back to the original function. Right? We're talking about points on the original function. So we need to state what that minimum value is. All you got to do at this point is take this value of 3, then plug back into your original function up here to get that value. So I've already done that calculation. If you take 3, you plug back in, you get a relative minimum of, I got negative 27. So we're trying to find where the function is concave up and concave down. Went through, found the first derivative, simplified all that. If I was going to go through again, right, take the derivative off the first to get to the second, the simplified form we would get Gave this to you earlier. You got 2x cubed plus 3x all over x squared plus 1 raised to the 3/2 power. All right, so if we're going to take the second derivative and figure out where this is concave up, concave down, and then figure out inflection points, what we're going to do, we're going to look at where this second derivative equals 0, and we're going to look at where this second derivative does not exist. Where the second derivative equals 0, now we're taking that numerator expression in that second derivative of 2x cubed plus 3x, setting that equal to 0 to solve. And to figure out where the second derivative does not exist, well, we're taking that denominator idea from the second derivative. We're setting that equal to 0 to solve. All right, on the equals 0 side, looks like I can factor out an x. If I factor out the x, I've got 2x squared plus 3 left. All of that equal to 0. Got two factors here that we can set equal to 0. Obviously, one of those factors, that x, would equal 0. Okay, now for the 2x squared plus 3 factor, we set that equal to 0 and we try to solve. You should notice that we're going to have some issues. Right? 2x squared is going to equal -3. X squared is going to equal -3/2. If you try to take the square root of each side, it's not going to happen. So the only solution we actually get from the second derivative being equal to 0 is this 0 value right here. Now likewise, on the does not exist side, we're going to notice there's some issues. Everything is raised to a power of 3/2 here, which basically means that this x squared plus 1 that's contained inside that power, that has to be 0. So trying to solve for x here, take your square root of each side, and once again, there's issues, right? You got the square root of a negative. So we do all that to find that we've got one value to play with. That one value is 0. All right, now, how we proceed from here. We set up a little chart. Got a column devoted to the x's. Then we're going to have 3 other columns. Second column is going to be devoted to the second derivative here. Third column, we're going to relate back to the original function. And then fourth column, we're going to discuss if we have any inflection points. So setting up your intervals for the x column. We're starting at -infinity. We're going up to any values we found here by letting the second derivative equal 0 or not exist. So only value we found was 0. We pause at 0, and we acknowledge what happens with the second derivative at 0. The second derivative equals 0 because that's how we found that 0 in the first place. And then we continue on going from 0 to infinity. Meaning I've got a really long chart here I don't need. All right, now we're going to complete the second derivative column by taking values on our intervals and plugging into the second derivative. So plugging back in here. Let's see what kind of signs we get back. So if I take a number for that first interval, if I'm going from -infinity to 0, so I choose -1 because I know that's less than 0, I plug back into the second derivative. The kind of value we get back, check me on this, but should be negative. And what that's supposed to mean to us about the original function, because remember, it all goes back to the original function. For the original function going to be concave down for that interval. So any curvature we see on that interval should have kind of this downward look to it. Now if we choose a number from 0 to infinity, something positive, say I choose 1 here, plug that back into the second derivative, should find that we get something positive back for that piece. So what that means about the original function, that means on that interval, the original function would have a curvature that's upwards. It's concave up. Now, if there is a change in concavity, there is an inflection point. So here, there's an inflection point where x is 0 because there was a change in concavity around x equals 0. And if there's an inflection point, we need to find what the original value of the function is. So we're going to take this value of 0, we're going to plug back into the original function, see what we get back here to establish that point. If you plug back into the original function, well, we find we get 0 back. So all this information here tells me something about the original function. It tells me something about the curvature on 2 intervals, and it tells me about an inflection point occurring basically at the origin here, right? When x is 0, the function is 0.